In this lecture, I am going to talk about the vibrational coarse structure. Vibrational coarse structure or progression in electronic spectroscopy. Vibrational coarse structure or progression in electronic spectroscopy. Okay, we already know that within each electronic energy level there will be a number of vibrational levels. We already discussed that in the previous video, right? So we already know that within a molecule there are electronic energy states, and there are vibrational states, and there are rotational states. Therefore the total energy of the molecule, that is E total, is equal to E electronic plus E vibrational plus E rotational. That is expressed in joules. And this, we know that this is known as the Born-Oppenheimer approximation because we have taken the sum of the electronic energy, vibrational energy and rotational energy in order to get the total energy, forgetting the fact that there are interactions between these different kinds of energies. Okay, and this is called the Born-Oppenheimer approximation. Born-Oppenheimer approximation. We already discussed this in the previous class, so I am not going to the details of that. And here we already know that the E electronic, that is much greater than E translational, okay, so E vibrational, which is much greater than E rotational. Okay, so we can say that the total energy E total is equal to E electronic plus E vibrational. We can neglect the last one, means the E rotational is very less compared to E electronic. Therefore, we can neglect this E rotational. Okay, so in fact we are considering here only the electronic energy and the vibrational energy. Okay, so when we are going to get some information from this one, it means some spectral information from this equation, we will be dealing with only the electronic transition and the vibrational transition involved in it. We are just neglecting the rotational transition. Okay, that is what this equation implicates. That is, during an electronic transition there will be accompanying vibrational transition, but there are accompanying rotational transitions also, but that rotational transition is just ignored. That is why it is written like E total is equal to E electronic plus E vibrational. Okay, all these are expressed in joules. And if we are expressing this in centimeter inverse, we can write epsilon total is equal to epsilon electronic plus epsilon vibrational. That will be expressed in centimeter inverse. So if we are expanding this equation, that is epsilon total is equal to epsilon electronic plus epsilon vibrational, with the known expansion for the epsilon vibration, we can write it like epsilon total is equal to epsilon electronic plus V plus half omega bar E plus minus V plus half the whole square omega bar E xc. Okay, here this is the expansion for the vibrational energy, right? V plus half into omega bar E minus V plus half the whole square omega bar E xc. Okay, here we have included this term also. This term is there because of the inharmonicity of the vibrator. Okay, And here V is the vibrational quantum number. We can have the values 0, 1, 2, 3, etc. X is the enharmonicity constant, and omega bar E, that is the equilibrium vibrational frequencies in terms of centimeter inverse. Okay, we already know all these terms. And in spectroscopy, there is a convention that the upper state will be represented by a single prime. So upper state will be represented by a single prime, and the lower state means lower energy state will be represented by a double prime. Okay, so we already know this because we used these notations when we were learning the vibrational rotational spectrum. Okay, so here also we will follow the same notation or same convention, that any upper state energy will be represented by the single prime, and the lower state energies will be notated by the double primes. Okay, and therefore we can write it like E prime electronic. It means that it is the upper electronic state, and E double prime electronic means it is a lower electronic state. If you see V prime, it represents that it is a vibrational quantum number in the upper electronic state, and if you see V double prime, it is the vibrational quantum number in the within the lower electronic state. Okay, so that is the convention that we are going to follow here. And now we can write the expression for the molecule, that is E total, for the upper state and lower state. Okay, we are considering two states, upper state and lower state. Within those two states, the transition is occurring. Okay, so in order to represent those states, you can just give the prime and double prime here. Okay, then we can represent those states. Now you know that the molecule will absorb the electromagnetic radiation, the UV or visible region, and then it will make a transition from the upper state to the from the lower state to the upper state. So we already know that within each electronic state there will be a number of vibrational states, right? There will be a number of vibrational states like this. So this is a lower electronic state, so we can write it like this is E double prime electronic, and this is the upper electronic state. Within that there will be many vibration states like this, so this is E prime electronic. So each of these states, okay, each of these lines, they are representing different vibrational states. Here it is V prime, and these are different V double primes. Okay, so the transition will be occurring from one lower state to one upper state. So within the lower state there are many vibrational states, and within the upper state there are many vibrational states also. Upper electronic state, there are many vibrational states also. So if the transition is occurring from the ground vibrational state of the lower electronic state or ground electronic state to where it can migrate, or to where it can make the transition, where it will land. Okay, where it will land means in the upper electronic state there are many vibrational states, and in which vibrational state here it will land, and that will be governed by the selection rule. And here the selection rule is that it is nothing but there is no selection rule. So for vibrational transitions there is no selection rule. Means the selection rule is that all V double prime to V prime transitions have the same probability are allowed. Okay, all V double prime to V prime transitions are allowed. They all have the same probability. So that is the selection rule. It means, in other words, you can say that there is no selection rule to govern a particular transition. So you can start from any vibrational state and land in any other vibrational state in the upper electronic state. So there is essentially no selection rule. So what will be the consequence of this one? There will be a number of transitions possible, okay, and there will be corresponding to these number of transitions, okay, you will get a number of lines, but not all lines will give enough intensity to be observed. This is because you already know that, for example, if you are considering the lower electronic state, only the ground vibrational state will be populated enough. You already know that the V is equal to 0 state and V is equal to 1 state. If you are comparing these two states, in the V is equal to 1 state, there will be only 1% population of what you can see in the V is equal to 0 state. So if you are considering all the molecules are populated between these two states, if you are just considering like that, then you will see 99% of the molecules will be in the V is equal to 0 state and only 1% of the molecule will be in the V is equal to 1 state. It means that when you are considering the transition from the ground electronic state to another electronic state, then you have to consider the transitions from the ground vibrational state itself, because most of the molecule will be occupying the ground vibrational state. So here V double prime is equal to 1, V double prime is equal to 0, that is the ground vibration state. The transition is starting from there. So if you want to get a simpler picture of the transitions, it is better that you consider the transitions from V double prime is equal to 0. It is a most probable, most populated state, and it gives appreciable intensity. So the lines with appreciable intensities will be obtained from the transition starting from V double prime is equal to 0 within the lower or within the ground electronic state. Okay. So this is what you can see here. See, here you can see that I have given the ground electronic state and the upper electronic state. Ground electronic state has double prime and upper electronic state has a single prime. And you can see that within the ground electronic state there are a number of vibrational states. See, V double prime is equal to 0, 1, 2, 3, etc. And also in the upper electronic state there are a number of vibrational states like V dash or V prime is equal to 0, 1, 2, 3, 4, etc. So now the molecule is ready to make a transition from the ground electronic state to the higher electronic state, next higher electronic state. So when it is making the transition, we can consider only transitions from V double prime is equal to 0, because only those transitions will give appreciable intensity. അതിൻ്റെ അർത്ഥം ഈ V dash is V double prime is equal to 0യിൽ നിന്ന് മാത്രമേ ട്രാൻസിഷൻ നടക്കൂ എന്നുള്ളതല്ല അതിൻ്റെ അർത്ഥം. ഈ V double prime is equal to 1ൽ നിന്നും ട്രാൻസിഷൻസ് പോസിബിൾ ആണ്, പക്ഷേ അവിടെയുള്ള പോപ്പുലേഷൻ വളരെ കുറവായതുകൊണ്ട് ഈ V double prime is equal to 1ൽ നിന്ന് ഒറിജിനേറ്റ് ചെയ്യുന്ന ട്രാൻസിഷൻ്റെ അല്ലെങ്കിൽ അതിൻ്റെ കറസ്പോണ്ടിങ് ആയിട്ടുള്ള സ്പെക്ട്രൽ ലൈൻ്റെ ഇൻറ്റൻസിറ്റി വളരെ വീക്കായിരിക്കും. അതുകൊണ്ടാണ് നമ്മൾ അത്തരം lines ഇപ്പോൾ കൺസിഡർ ചെയ്യാത്തത്. So we will consider only the intense lines, and those intense lines will be originating from the transitions from the V double prime is equal to 0. So there is no selection rule. It means that the transitions which are originating from this level can land in any vibrational state in the upper electronic state. So it can land in V prime is equal to 0 like this. It can land in V prime is equal to 1 like this. Or it can land in V prime is equal to 2 like this. V prime is equal to 3, V prime is equal to 4, V prime is equal to 5 like that, right? So the transitions starting from here are landing in any vibrational state in the upper electronic state. So corresponding to that, you will get n number of lines. So this is a spectral line. This corresponds to the V double prime is equal to 0 to V prime is equal to 0. Okay, that is called a 0-0 transition. 0-0 transition. So these transitions, each transition or each spectral line originating from a particular transition can be represented as V prime, V prime, V double prime. Okay, V prime, V double prime. So that is 0-0. And here it is starting from 0 and ends up in 1. So we can call this as 1-0 transition. And here it starts from 0 and ends in 2. Okay, so it is a 2-0 transition. So there are a number of transitions like 0-0, 1-0, 2-0, 3-0, 4-0, 5-0, etc. Okay, and now you can look at the energy of these transitions. This is the 0-0 transition. There is a particular energy for this transition, and corresponding to that energy we will get a wave number in centimeter inverse, and in the spectrum you will get a line corresponding to that wave number. So this is that line. And when you consider the 1-0 transition, and there will be a particular wave number for that also, and that wave number is greater than the 0-0 transition's wave number. So you will get a line which is at a higher centimeter inverse in the spectrum, that is this line. And when you are looking into the next one, that is 2-0 transition, then its wave number is greater than the second one. So you will get a line here. And when you are looking at the 3-0 transition, its wave number is still higher. 4-0 is still higher. 5-0 is even more higher, right? So you will get a series of lines. But here you can see that in the vibrational states, the vibrational states are not equally spaced. It would be equally spaced if the vibration is simple harmonic. But you know that in the real molecules, the vibration will not be simple harmonic, it will be enharmonic vibration. Because of the enharmonicity, the vibrational levels are getting converged when we are going to the higher vibrational states, right? അപ്പോൾ നമ്മൾ മുകളിലോട്ട് പോകുന്തോറും ഈ വൈബ്രേഷണൽ സ്റ്റേറ്റ്സ് തമ്മിലുള്ള അകലം കുറഞ്ഞു വരികയാണ്. അതുകൊണ്ട് ഇവിടുത്തെ ഓരോ ട്രാൻസിഷൻ നമ്മൾ പരിഗണിക്കുമ്പോൾ ആദ്യത്തെ ട്രാൻസിഷനും രണ്ടാമത്തെ ട്രാൻസിഷൻ തമ്മിലുള്ള എനർജി ഡിഫറൻസ് അതിനേക്കാൾ കുറവായിരിക്കും രണ്ടാമത്തെയും മൂന്നാമത്തെയും ട്രാൻസിഷൻ തമ്മിലുള്ള എനർജി ഡിഫറൻസ്. കാരണം അതിന് കുറച്ചും കൂടി ഡിസ്റ്റൻസ് കുറച്ച് ചാടിയാൽ മതി അല്ലേ. അപ്പം ഇവിടെയാണെങ്കിൽ ഈ എനർജി ലെവൽ അല്പം കൂടെ താഴ്ന്നിരിക്കുകയാണ്, അതുകൊണ്ട് അതിന് അല്പം കൂടി എനർജി ഉയർന്നാൽ മതി. ഇവിടെയാണെങ്കിൽ എനർജി ലെവൽ വീണ്ടും താഴ്ന്നു എനർജി, അതുകൊണ്ട് അല്പം കൂടി എനർജി ഉയർന്നാൽ മതി. അതായത് നമ്മൾ ഈ സീരീസ് ഓഫ് ട്രാൻസിഷൻസിനെ നമ്മൾ പരിഗണിക്കുമ്പോൾ when we are going for the higher and higher wave numbers, you can see that the lines will come closer and closer, and finally you will end up in a continuum, so that the lines will touch each other. Okay, so that is the case what you can see here. And now here we have a series of lines, and each line in the series is represented by V prime, V double prime. Okay, and in all these cases V double prime is equal to 0. But V prime is increasing by 1. Here V prime is 0, here is 1, 2, 3, 4, 5, etc. Right? So V prime values are keeping on increasing. Okay, therefore we can call this as V prime progression. V prime progression. Okay, so this is a V prime progression. So why it is called a V prime progression? Because in these transitions the V primes are increasing by unity. When you are considering each line in the spectrum, the V prime values are increased by unity. When we are going from one line to the next line, it is increased by a unity. Therefore you can call this as V dash progression or V prime progression. Okay, so this is called the progression, or this is called the vibrational coil structure of the electronic spectrum. Actually what is going on here there is a transition from one electronic state to the next higher electronic state. So the UV visible radiation is absorbed here. Okay, but within that transition Within that mechanism, there is a vibrational transition also. Okay, starting from a particular vibrational level, it ends up in different other vibrational levels in the upper state. Okay, so the number of lines are obtaining here because of the vibrational transitions or accompanying vibrational transitions. That is why this is called the vibrational coarse structure. Vibrational coarse structure. If the electronic states had no vibrational states inside, then you would get only a single line. But here, instead of the single lines, you are getting a series of lines. And you are getting a series of lines because each electronic state will have a number of vibrational states inside. And that is why you get a series of lines. Okay. And this is called the vibrational coarse structure. Vibrational coarse structure. Or we can call this as progression. Okay. Progression. Particularly, this is called V prime progression or V dash progression. Okay, now you got an idea of how the vibrational coarse structure is originating. Okay, so if you are calculating the new bar or wave number of each of these transitions, we can go for calculating the wave number of each of these transitions. Okay, so how can we calculate the new bar of each of these transitions? We already know that in this case delta E total or delta epsilon total is equal to delta E electronic plus delta vibrational, delta E vibrational, right? Vibrational. Okay, so delta E total, that will be obtained in centimeter inverse. So from here you will directly get the wave number of the spectroscopic line. So you can read it as nu bar spectroscopy because wave number has the same unit of centimeter inverse, right? So whatever value you are getting here, delta E total, delta epsilon total, that will be in terms of centimeter inverse, and that will be corresponding to the line, the wave number of the spectral line. So we can call it as nu bar spectroscopic. That is equal to delta E electronic. That means upper electronics energy minus lower electronic energy. That is epsilon prime minus epsilon double prime. Okay. That is delta E electronic plus delta E vibrational or delta epsilon vibration. So what is delta E vibration? That is the energy of the upper vibrational state, means energy of the vibrational state in the upper electronic state minus energy of the vibrational state in the lower electronic state. Okay, so that is equal to energy of the upper vibrational state, that is V prime plus half into omega bar E. Okay, here we have to consider that here omega bar E is for the lower vibrational state, so that is why I get omega bar E prime. Okay, minus V prime plus half the whole square, V prime plus half the whole square. Okay, omega bar E prime xc, omega bar E prime xc, and I have to give a prime for xc also. Okay, because all these are belonging to the upper vibrational state, that is why it is given prime in all these terms, minus the energy of the lower vibrational state. So let me write this is in bracket. This is the energy of the upper vibrational state minus the energy of the lower vibrational state. That is equal to V double prime plus half, okay, omega bar E double prime minus V double prime plus half the whole square omega bar E double prime xc double prime. Okay, so that is the energy of the lower vibrational state. So now you may be wondering why we are giving double prime to omega bar E and also Xc. Okay, actually you can see that in the upper vibrational state. Okay, for example, we have shown here the upper vibration states and lower vibrational state. And these are the vibrational states in the ground electron. You suppose that this is a ground electronic state. Okay, E double prime electronic is the ground electronic state. So in the ground electronic state of the molecule, there are a number of vibrational states. And corresponding to those vibrations, there will be an equilibrium vibrational frequency, that is omega bar E in the ground, omega bar E in the ground electronic state, okay, omega bar E. And there will be an enharmonicity constant, that is Xc. Okay, so since it is in the ground electronic state, let me give a double prime here and Xc double prime here. Okay, and we have the omega bar E and Xc in the upper electronic state also, because in the upper electronic state there are a number of vibrational states, and corresponding to that there will be equilibrium vibrational frequency and enharmonicity constant. Now the question is that whether, since it is in the upper electronic state, we can give it as omega bar E and Xc bar prime, single primes. Now the question is that whether W bar E prime is equal to W bar E double prime, that is the question, or Xe bar is equal to Xc double prime. Okay, Xc prime is equal to Xc double prime, that is a question, whether it is true or not. Actually, they are not equal. Omega bar is not equal to omega bar E prime is not equal to omega bar E double prime, and Xc prime is not equal to Xc double prime. This is because you can see that in the ground electronic state there will be a particular bond length for the bond that we are considering. നമ്മളൊരു ബോണ്ടിന്റെ vibration അല്ലേ കൺസിഡർ ചെയ്യുന്നത്, അതിനൊരു particular bond length ഉണ്ട്. But when the molecule is excited, means when there is an electronic transition, the molecule is excited. Excited molecule in the case, അതിന്റെ bond strength എന്ന് പറയുന്നത് ഗ്രൗണ്ട് ഇലക്ട്രോണിക് സ്റ്റേറ്റിലെ ബോണ്ട് സ്ട്രെങ്ത്തിനേക്കാൾ കുറവായിരിക്കും. എന്ന് പറഞ്ഞാൽ ഇലക്ട്രോണിക് സ്റ്റേറ്റ്, എക്സൈറ്റഡ് ഇലക്ട്രോണിക് സ്റ്റേറ്റിൽ മോളിക്യൂൾ കുറേയും കൂടെ എന്തായിരിക്കും, അൺസ്റ്റേബിൾ ആയിരിക്കും. അതായത് the whatever bond strength was here, that bond strength will not be here. That will be a different bond strength in the upper electronic state. So the bond strength can be represented by the force constant K. Okay, and there is a particular force constant K in the ground vibrational state. Let me call this as K double prime. And here the force constant K will be different because the force constant K represents the bond strength. So K prime will be different from K double prime. അല്ലേ, താഴത്തെ ഫോഴ്സ് കോൺസ്റ്റന്റ് എന്ന് പറയുന്നത് ഒരു ഉയർന്ന ഫോഴ്സ് കോൺസ്റ്റന്റ് ആണ്, കാരണം ഇവിടെ ബോണ്ട് സ്ട്രെങ്ത് കൂടുതലാണ്. മുകളിലത്തെ ഫോഴ്സ് കോൺസ്റ്റന്റ് K പ്രൈം എന്ന് പറയുന്നത് K ഡബിൾ പ്രൈമിനേക്കാൾ താഴ്ന്ന ഒരു ഫോഴ്സ് കോൺസ്റ്റന്റ് ആണ്, ബിക്കോസ് ദ ബോണ്ട് സ്ട്രെങ്ത് ഈസ് യൂഷ്വലി ഡിക്രീസ്ഡ് ഇൻ ദ അപ്പർ ഇലക്ട്രോണിക് സ്റ്റേറ്റ്. ഓക്കെ, അതുകൊണ്ട് ഇവിടുത്തെ K ഡാഷും അല്ലെങ്കിൽ K പ്രൈമും K ഡബിൾ പ്രൈം, K prime is not equal to K double prime. That is very obvious. K prime ഉം K double prime ഉം obvious അല്ല എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ അതിൻ്റെ അർത്ഥം അതിൻ്റെ ഇക്വിലിബ്രിയം വൈബ്രേഷണൽ ഫ്രീക്വൻസിയും ഡിഫറൻ്റ് ആണെന്നർത്ഥം. കാരണം വൈബ്രേഷണൽ ഫ്രീക്വൻസി എന്തിനെ ഡിപ്പെൻഡ് ചെയ്തിരിക്കുകയാണ്, ഫോഴ്സ് കോൺസ്റ്റന്റിനെ ഡിപ്പെൻഡ് ചെയ്തിരിക്കുകയാണ്. We have already learned the equation for that. The vibrational frequency is depending upon the force constant. Since the force constants are different in both electronic states, the vibrational frequencies will be different. So we have the answer that omega bar E prime is not equal to omega bar E double prime. And also the same thing can be guessed here also. Here this is the oscillator with the lesser bond strength or lesser force constant, Here it is an oscillator with the greater force constant or greater bond strength. So in both cases, then harmonicity will be different. So Xc bar will not be equal to Xc bar prime will not be equal to Xc prime will not be equal to Xc double prime. So that is why it is important that when we are writing the expression for this expression for this new bar spectroscopy, we have to be very careful that we have to give prime and double prime for these parameters, that is omega bar and Xc, because these parameters will be different in both states. Okay, so that is very important. Now we have an expression for the wave number of the spectroscopic line, okay, or wave number in the line appearing in the spectrum. So any line what is seen in this progression, its wave number can be calculated from this particular equation. Okay, and so if you are getting a decent number of lines in the band, here we can consider this as a band. Why this is called a band? This progression can be considered as a band. Why it is considered as a band? Because usually these lines will be very diffuse and wide. Okay, usually they will be very diffuse and wide, and that is why it is called as a band also. Okay, and so when we have a considerable number of lines within this band, okay, and for example if you have half a dozen lines observed in this band or vibrational coarse structure or the progression, if you have enough number of lines here, then we can calculate these parameters from those lines. Means we can calculate omega bar E prime, Xc prime, omega bar E double prime, Xc double prime. Okay, these parameters can be calculated if you have enough number of lines. Okay, for each line will give the new bar spectroscopy. Okay, so this equation can be solved to get these parameters. So here one thing is very important. Okay, here the epsilon prime minus epsilon double prime, what is that? That is the difference in the electronic energy levels, right? And the omega bar and omega bar Xc bar are the vibrational frequency and enharmonicity constants in the excited electronic states, right? And omega bar double prime and Xc double prime are vibrational frequency and the enharmonicity constant in the ground electronic state. Okay, and here omega bar prime and Xc bar, these are in the excited electronic state. Okay, these are in the ground electronic state. Okay, so normally this is very difficult to get these parameters. Omega bar and Xc in the excited electronic state, these parameters are very difficult to be drawn from a simple vibrational spectrum. Okay, for example, you are exciting a molecule and then you suppose that that molecule is in the excited state for some time. Okay, it means that the electron is excited from the ground orbital or excited from the normal orbital, and it is going to a higher orbital and staying there for some considerable amount of time. You just suppose that. Okay, if it is staying in the upper electronic state for some considerable amount of time, then you can measure the vibrational spectrum of the excited electronic state. Okay, so you can just do the IR of that molecule when that molecule is simply sitting in the upper electronic state. You just suppose that is happening. Then in that case we can extract these parameters. What is that? The omega bar and Xc in the excited electronic state. So this is just an imagination. That is a good story. But this story is almost impossible. Because once the molecule is excited from the ground electronic state to the next higher electronic stage, okay, and that usually the higher electronic states are, the lifetime of the molecule, the higher electronic states are very less, okay. So within a very short span of time, this excited molecule will come back to the ground state. So the molecule will not stay in the excited electronic state for a long time. So we cannot perform the IR spectrum in order to extract these parameters in the excited state. So that is practically impossible. ഇപ്പോൾ ഒമേഗ ബാറിയും എക്സിയും എക്സൈറ്റഡ് സ്റ്റേറ്റിലുള്ള ഒമേഗ ബാറിയും എക്സിയും നമുക്ക് എക്സ്ട്രാക്ട് ചെയ്യാന്നുള്ളത് പ്രാക്ടിക്കലി ഇമ്പോസിബിൾ ആണ്. കാരണം എക്സൈറ്റഡ് സ്റ്റേറ്റിലുള്ള മോളിക്യൂളിൻ്റെ ലൈഫ് ടൈം വളരെ കുറവാണ്. അതുകൊണ്ട് നമുക്കൊരു ഐ ആർ ട്രാൻസിഷൻ സ്റ്റഡി ചെയ്യാനുള്ള ലൈഫ് ടൈം ഒരിക്കലും കിട്ടത്തില്ല. ഓക്കെ, അപ്പോൾ ഈ പാരാമീറ്റേഴ്സ് നമുക്ക് നോർമലി ഐ ആർ സ്പെക്ട്രോസ്കോപ്പി ഉപയോഗിച്ചുകൊണ്ട് ഈ പാരാമീറ്റേഴ്സ് നമുക്ക് എക്സ്ട്രാക്ട് ചെയ്യാൻ കഴിയില്ല. പക്ഷേ നമുക്ക് ഇലക്ട്രോണിക് സ്പെക്ട്രോസ്കോപ്പി ഉപയോഗിച്ചുകൊണ്ട് ഈ പാരാമീറ്റേഴ്സ് എക്സ്ട്രാക്ട് ചെയ്യാം എന്നുള്ളതാണ് നമ്മളിപ്പോൾ പഠിച്ചത്. സോ just by analyzing the electronic spectrum of the molecule or the progression the vibrational coarse structure or the V dash progression or V prime progression or the band structure, we can just calculate the parameters, the vibrational parameters in the excited electronic state. That is a very important thing. Okay, and now finally I want to mention something else. Now you know that the spectral lines are obtained because of the excitation of the molecule from one electronic state to the next higher electronic state. Okay, and here the energy is getting absorbed. In order for this transition to occur, this type of transitions to occur, the energy should be absorbed. Okay, so what you are getting here is an absorption spectrum. This is an absorption spectrum. But you consider the emission spectrum. Emission spectrum means the first the molecule is excited, and once the molecule is excited, then it will come back to the ground state, giving off the radiation. That radiation, which is given off by the molecule, will be harvested, and then you can get a spectrum. That will be the emission spectrum. Okay. So in order to get the emission spectrum, first you have to excite the molecule to the excited stage, and after that you have to harvest the lines due to the de-excitement. Okay, the molecule will come back to the ground electronic stage. So when it is excited, some molecules will be in this state, some other molecules will be here, some other molecules will be here, some other molecules will be here and here. So quantum mechanics says that there are equal possibility for these transitions. Okay, and so the molecules are distributed in different vibrational states in the upper electronic state during the excitation. So when it is de-excited, okay, so where it will land? It is starting from V prime is equal to 0, 1, 2, 3, 4, 5, etc. Okay, അപ്പോൾ അവിടെ അവൈലബിൾ ആയിട്ടുള്ള മിക്ക വൈബ്രേഷണൽ സ്റ്റേറ്റ്സിൽ നിന്നും ട്രാൻസിഷൻ താഴേക്ക് സ്റ്റാർട്ട് ചെയ്യുന്നു. പക്ഷേ എവിടെ വന്ന് വീഴും? Since there are no selection rules, it can fall anywhere, right? It can fall not only at 0, it can fall at 1, it can fall at 2, 3, 4, 5, etc. So when you are considering the emission spectrum, you will get a number of lines. Okay, the transition which is starting from V prime is equal to 0 can end up in a number of vibrational states in the lower electronic state. It can end up in V double prime is equal to 0, 1, 2, 3, etc. And the transition starting from here can also end up in a number of vibrational states. The transition starting from here can also end up in a number of vibrational states. So even if you are getting 1, 2, 3, 4, 5, 6 intense lines in the absorption spectrum, that will not be the case when you are studying the emission spectrum. When you are studying the emission spectrum, you will get a number of lines. Instead of the 6 lines, you can get a multiple of the 6. Okay, each of these excitation, each of this excitation will land the molecule in different vibration states in the upper electronic state, and all these molecules can come back and it will end up in a number of vibration states in the lower electronic state, and therefore you will get a many number of lines when you are studying the emission spectrum. So emission spectrum is not going to be simpler like the absorption spectrum. So if somebody is asking you why the electronic emission spectrum are much more complicated than the absorption spectrum, this is the answer. Different B prime states will be populated already during the first excitation, so it will have so many V double prime states to revert back. So you will get a number of lines, and the spectrum is going to be much more complicated. Okay, so I hope that I have given you some considerable amount of information on this vibrational coarse structure of the electronic spectrum. Okay, now you know what is vibrational coarse structure, how it is originating, and you know that this is also called a V prime progression, and it is also called a band. Okay, so you know the properties of this excitation, and you know what will be the case when you are considering the de-excitation. Okay, so I hope you understood this portion. If you have any doubt, please don't hesitate to ask me. Thank you for watching, and stay tuned.